Hello everyone, and welcome to lecture 3. So today we're going to continue our discussion about open system dynamics of quantum mechanics. Just to recall, in the first lecture we covered the kinematics of quantum mechanics. How do we describe states of quantum mechanics? And in the second lecture we covered the dynamics of quantum mechanics, and we ended with the beginning of a discussion about how do we describe the most general possible dynamical processes in quantum mechanics. So this is the picture, as I said last week, or the week before actually. This is the picture that I will draw throughout this course. You have some system that you can control, under your control, and you have the rest of the universe, which is some kind of environment. And our task is to describe just this. How does this small part of this bigger quantum system behave as time passes? And we can model every experiment in this way. We have here, cis could stand for everyone in this room. Cis could stand for a single atom that you've isolated. Cis could be the planet Earth or a black hole. But outside of cis, there's something else, unless cis happens to be the whole universe, which we won't do in this course. And that is what we're going to call the environment. And our task is to just describe what does the system do. Now, according to the postulates of quantum mechanics, a closed quantum system undergoes unitary evolution according to Schrödinger's equation. And the way we generate time evolution is to simply solve Schrödinger's equation for the propagator, or the unitary that implements the dynamics. And the equation of motion you have to solve is this one. Okay, so this is standard quantum mechanics. This is how closed quantum systems evolve. But as you are no doubt aware, normal systems that we interact with every day are not closed. There is this environment, which could be some electromagnetic field you cannot isolate from the system, or some vibrations in the room, or any number of possible other sources of noise. And even though the whole system as a collective entity undergoes unitary evolution, because this line here indicates that the system plus environment is a closed quantum system, if we want to describe just the system itself in isolation without having to talk about the environment, then unless this U is pretty simple, something's going to happen, right? And I can exploit just physical intuition right now to give you a sense of how we need to have some more general notion of dynamics for systems that are embedded in composite systems. Just think about this system being a cup of water on the table, which is interacting with the electromagnetic field, which is interacting, even particles are coming into the cup of water, particles are coming out of the cup of water as they evaporate, and impurities are being absorbed onto the surface and so on. So the cup of water by itself is something we might want to describe by itself without having to deal with the rest of the environment. I think that's a reasonable thing to want to do. We don't want to, when we talk about the cup of water, we don't want to have to describe the positions of all the particles in the universe. So that's why we want to find a way to talk about the cup of water as though it was an independent quantum system. But to do that requires that we go outside of the sets of evolutions that are allowed by Schrödinger's equation. And that's what motivated us in the previous lecture to discuss more general types of evolutions in quantum mechanics. In fact, we asked, what's the most general kind of evolution allowed in quantum mechanics? And the answer that we discussed in the previous lecture was to proceed first axiomatically, just to say, well, what's the minimum we require of an evolution? And we settled down on two axioms. Number one, so this is in the Heisenberg picture, right? You can adapt all of this to the Schrödinger picture, but it's a little bit easier to do it in the Heisenberg picture. So the first thing that any putative evolution of a quantum mechanical system has to satisfy is this. And this just simply says that probability is conserved. And the second axiom that any possible evolution map would have to satisfy is that it is completely positive. So that's the second thing we discussed. And what this means in physical terms is that if you describe an evolution for a system A, and that's a legal quantum mechanical evolution, then it better be the case that if I bring in some other system, don't interact with it, and then take that other system away, that the global map describing that ought to be a valid quantum mechanical evolution as well. Now, this second thing seems so obvious you might not even think to turn it into an axiom. But there's a classical counterexample which shows us that this is a non-trivial constraint. So where's the data here? So E is a map from the observables describing the output system B to the observables describing the input system A. IN is the identity channel. For a N or an N level system. So this thing here, this object here, is a channel, is a dynamics describing your original dynamics plus an additional n-level quantum system that you just brought in. And that's it, actually. Well, this has to be true for all n. That's the only quantifier I'm missing here. So I'll stick a for all n there. And that's the bare minimum you might require from any map claiming to be a valid evolution of a quantum system, open or closed or otherwise. So if you look at unitary evolutions, the ones generated by Schrödinger's equation, let's check, do they satisfy these two conditions? We should be able to do this without actually doing very many calculations at all. So if E is corresponding to a unitary evolution, then E is just U, I, U dagger, or U dagger I, U, whichever way around you want to do it. Does that preserve the identity? Well, U times U dagger is the identity, so yeah, that one's straightforward. Is this positive? Well, if you put in a positive operator and do U, well, maybe I do have to write something for this. Okay, right? This is something that had better be a legal quantum mechanical evolution, otherwise we messed up our axioms, right? So let's check. 1 is u I dagger equal to I. Well, the answer is yes, because that's what it means to be unitary. And the second one is we want that E tensor, the identity channel, the do-nothing channel, is positive. So I use this symbol here to denote that it's positive. And what does that mean? Well, that's the case if and only if for all effects E, it goes from B to A. So all possible valid outcomes of a quantum mechanical measurement we must have that this object here, this matrix, if this is a finite dimensional system, is a positive matrix. That's what the second axiom requires for all n, right? Not just for one n, but for every integer n, for every possible ancillary system you could add in. And let's check, is this the case here? Well, this channel, what does it look like? It looks like if you apply this channel to this effect, then that's the same as conjugating by this unitary here. The identity is a unitary. This is a n by n matrix. And some unitary tensor, some unitary is unitary. So this overall thing is unitary. Since unitaries don't change the spectrum of an observable or an operator like this, then if it was positive before, then it's actually positive afterwards. And if you don't like to use the spectrum, then just simply write E as x dagger x. And then you can see that the result of having applied the channel to an operator of the form x dagger x gives us another operator of the form x prime dagger x prime, where x prime is, well, x conjugated by this unitary. So indeed, if it takes a positive effect for this composite system here is mapped to a positive effect. So unitaries, reassuringly, are in fact valid dynamics according to these two axioms. But it turns out that there's actually more than just these two. And that's what allows us to model parts of quantum systems without having to model the whole environment. And what we're going to show today is that this axiomatic approach here is equivalent in a restricted setting to a constructive approach, where you just simply build up all the operations you think that are allowed in quantum mechanics by hand. And we'll see that this way of characterizing operations is exactly equivalent to this other way, where you just simply enumerate the possible dynamics that you will allow in a quantum mechanical system. It's not completely one-to-one, unfortunately, but it's close enough. So, and here's an alternate approach to defining the most general dynamics allowed in quantum mechanics. And we're going to discuss this alternate approach for a bit, and then we're going to show that these two are equivalent in a certain restricted setting. And the idea is here, in this alternate approach, is simply to, as I said, enumerate what you think should be allowed. So we're just going to enumerate the allowed operations in quantum mechanics. And then we're going to see what we can build with these allowed operations. So the first one first allowed operation in quantum mechanics is if we have a system in a specific state, then an allowed operation is to bring in another quantum system in a specific state. I mean, that really better be allowed, right? And the way we describe that in the Schrödinger picture is if your system A is in the state omega, you are allowed to build a bigger system by adjoining a quantum system in the state sigma. That's an allowed operation in quantum mechanics for all sigma. And the operational picture that we have for this is that if you have the state omega, which I represented with this diagram here, then you're allowed to take that state and build a bigger state, omega tends to sigma, of the system A, B. So that's an allowed operation in quantum mechanics. So as written there, this operation is not resulting from unitary dynamics because you have a state of a smaller system being transformed to a state of a bigger system. So this is not unitary as written. It doesn't come from solving Schrödinger's equation. Of course, you can argue, well, you know, that system B was always there. All I did is do nothing, right? So that's one perspective you can take. And if you always want to enlarge your description to include everything in that fashion, then everything will turn out to be a unitary process. But for the purposes of describing or discarding parts of a system, so you can say get rid of the environment when you want to describe your quantum system, it's convenient to allow this as a separate operation. So the second thing we're going to allow is, well, unitary transforms, right? That's one of the original postulates of quantum mechanics. That's allowed. So in a unitary transformation in the Schrödinger picture, you take some state and you map it to some other state. So this calligraphic U of x means conjugate with some unitary. Except we're working in the Schrödinger picture, so let's do that. Okay, that's simply allowed because we postulate that that's an allowed operation. And the third and final allowed operation in quantum mechanics is to reduce to a subsystem. And what that means operationally is we simply do not measure things on the other system. If we have some state on a composite quantum system, a system comprised of two subsystems, then we are allowed to ignore system B. If we just simply say we're never, ever going to measure anything on system B, then we must be allowed to talk about the state on system A. What's the transformation that takes this bigger state to an effective state on just A? It's better be allowed. So we could call this the effective state or reduced state. We had encountered this before. And the way we build this effective state is by only writing down those numbers that correspond to non-trivial measurements just on A and ignoring B. So those are three, I hope, fairly reasonable operations that should be allowed to us in quantum mechanics. And the remarkable thing is, with just these three operations, we can build up the most general possible operation allowed according to these axioms of quantum mechanics. And we'll prove that in the finite, well, we're not going to prove it actually, I'm just going to quote the result. In a finite dimensional case. So just I'll draw a couple of pictures now of how we can mix and match these three types of operations to build fantastically complicated things. Okay, I guess I'll leave these two boards here and do that underneath. So the point is we've got three atomic or fundamental operations we're allowed, and we're going to mix and match and compose them, and put them together. That's also allowed. So I'm just going to draw a graphical example. We could start with some state of, for example, a qubit, and then adjoin another qubit in a state sigma, sort of like giving us a bigger effective state of a composite quantum system, AB, say 2 qubits. This is A, now this is AB. And then this could be like step 1. In step 2, we do some unitary evolution on the joint system now. That's also allowed. And that builds us a effective state of, again, just AB, but it's a different state now. So it's And in step 3, we could adjoin another system. In the state sigma C. And then, which builds us an effective state of a tripartite system. And then in step 4, we could do some evolution on just B and C and do nothing to A. Let's call this V. Could be a different unitary. And then we could throw out system A by simply ignoring it. That's this third possible allowed operation where we simply ignore a system. Oh, I didn't draw down the picture for that. I tend to represent that as just a cross. And so then we finally end up with some effective state of the system BC. So these were all allowed operations in quantum mechanics according to this constructive alternate approach. And we're going to show in a second, or not show, but I'm going to quote the result to you, that the kinds of operations you can achieve by composing these operations correspond exactly to this axiomatic approach here, where you just say, we allow any operation in quantum mechanics which obeys this. This is unfortunately only true for finite dimensional systems, but this is still a pretty cool result. So this is how you build up arbitrary operations in quantum mechanics according to this constructive approach. Let me now quote this result to you, and then we will move in the second part of this lecture to the description of many particle systems. The most amazing result in this whole business, I think, is a theorem due to Steinspring, which proves that these two ways of dealing with quantum dynamics of quantum systems are equivalent. I'll quote to you now the theorem. I'm not going to prove it today, although actually the proof isn't ridiculously hard. It's fairly concrete. Takes less than a page. So let E be a valid CP map. This is to say it's a linear map which preserves the identity and which is positive when you tensor on identity channels. And we're going to allow the possibility that this map takes you from a smaller system to a bigger system, or from a bigger system to a smaller system. So instead of this being an N here, we're going to make that an M. M subscript little m. Then there's some L and some operator operator such that Yep.
What means is CP?
Oh, CP, sorry, I didn't define that. Completely positive. CP means completely positive, which means any map satisfying 1 and 2. So this is Stine-Springs theorem. What does it say? It says that if you have some completely positive map, which is a map satisfying axioms 1 and 2, then you can always find an operator V going from Cm to Cn tends to Cl such that this map E is equivalent to taking, this is now in the Heisenberg picture by the way, I'll say that in a second, taking an effect of the form x tensor I, do the operation V, and then you get an effect on your input system. So should specify somewhere this is in the Heisenberg picture. Now it doesn't look exactly like it, but it turns out that this representation here is equivalent to a composition of 3 of these allowed operations here. So I'll draw a picture that explains that in one moment. So this operation V is not a unitary, it's an isometry. So I will write that down. And then I'll draw a picture of what this theorem says. So you can take the precise statement of the theorem here, or you can remember the picture. And for this course, the picture's already sufficient. So firstly, though, I have to clarify that V dagger V is the identity. And then I will draw a picture representing this theorem. So if you have an the first thing to observe is that an isometry is really just a unitary acting on a bigger space where you ignore some part of that bigger space. So if you have some isometry V, V takes some m-dimensional vector to some n tensor L times L dimensional vector here, then that's always, you can always write that as a unitary, where you have some input state 0 actually, awkwardly, it's not quite always the case. If n times L doesn't equal m times the dimension of this space here, it doesn't work. I'm going to just sort of brush over this detail. So every isometry, as long as these numbers are correct, you can think of it as just a unitary on a bigger space where you have some additional degrees of freedom in a specified vector like that. There's a way to fix this with direct sums, but let's just pretend that m times the dimension of this additional system here is exactly equal to n times this L here. Now, since that's the case, then what this theorem here is actually saying is that every CP map on a finite dimensional system like that, so every possible allowed transformation according to this first approach, this axiomatic approach here, you can represent any such transformation as a unitary as in, this is now in the tediously in the Schrödinger picture, so I'm afraid in this course you'll have to get very good at just flipping between these two pictures. So E star means exactly the map E, but in the Schrödinger picture. Or let's just use E dagger, just to be consistent with the previous lectures. Every transformation allowed by quantum mechanics described in the Schrödinger picture can be written as tensoring in an additional system in some state 0, or in this case phi, some unitary operation, followed by reduction to a subsystem. So there's 3 steps. Tensor in a new ancillary subsystem in a state phi, perform a unitary operation, finally reduce to a subsystem. And those are exactly the 3 allowed operations that we described. So this is tensor, ancillar, this is unitary, and this third step is reduction. So this theorem, this is a truly remarkable theorem. It says that if the bare minimum you demand from a quantum dynamics is that it satisfies these 2 axioms, then any such map that satisfies these 2 things here actually can be written as a composition of 3 of these allowed operations of quantum mechanics. And this is what allows us to describe all allowed operations in quantum mechanics by simply forgetting these conditions for the most part. We often just talk about the allowed operations in quantum mechanics as being combinations of unitary evolutions and reductions to subsystems, meaning what I said at the beginning of the lecture is that your system is prepared in some state that's uncoupled with the environment, it interacts with the environment, and then you throw away some part of the system. Sadly, this theorem is only true for finite dimensional systems, which is a bit of a pain because we're going to talk about infinite dimensional quantum systems even today. Now, that is sort of throws up some interesting philosophical questions, such as, are there processes that we should allow in quantum mechanics that can't be written as a composition of tensoring in something, some Schrödinger dynamics, and some tracing out? The answer is yes, there are processes that can't be written that way for infinite dimensional systems. And that's an interesting observation, I think, because although we won't really encounter this in our course, because we're always going to have some closed system in the back of our minds. We'll have, say, an atom and the electromagnetic field, and we'll just always think about that as a closed system. There are cases where you might wonder if there are dynamics allowed in quantum mechanics that don't allow you to have a bigger closed system. And one example that's currently very controversial and creating a lot of discussion is that of a black hole. So if you have a quantum system with describing a black hole, should you think of that as just the unitary dynamics of some bigger thing, right? You know, the stuff that goes in the black hole is not destroyed but hangs around somewhere? Or could it be that the dynamics of the universe is fundamentally irreversible, that it preserves the identity, so probability is conserved. It preserves positivity, so legal measurements are still legal measurements after this dynamics occurs, but that something really is lost. Now, there's lots of arguments about that in the literature right now, and the jury is definitely out on this topic. But it's allowed. I want to stress that it is possible for infinite dimensional systems to have dynamics that are irreversible, but yet do not admit a description like this. In contradiction to what you might have heard, which is that you might have heard people declare that the only possible way to conserve probability in quantum mechanics is by unitarity. So that's what they're referring to is essentially the Steinspring result here, because the only thing that's really non-trivial in this whole story is this U here. I mean, the tensoring in bit is not really any dynamics, and the ignoring something is not really any dynamics. And so the reason probability is conserved is sort of this U part here. But if you don't get to use this representation, then it becomes non-trivial. It is possible to have dynamics of quantum systems that are not unitary, that yet still preserve probability. So I want to stress that point strongly because you will hear people declare the opposite. And then the next stage is that they will say, oh yes, well that's true, but that's not consistent with Lorentz invariance. So you might see it written, or you might hear people say that the only way to preserve Lorentz invariance and conserve probability is by unitary dynamics like this. This also turns out to be false. Although I can't give you the paper because it's still unpublished from a colleague of mine. You'll just have to believe me, which is there is an example of a system which has Lorentz invariance, which conserves probability, and which you cannot write like this. I claim this is a true statement, but you just have to believe me.
I have one more question about the Steinspring.
Yes, please.
Is there any relation between N, M, and L? Do we know, like, L is the...
Oh, what is L in this? Yeah, so N, so the question is roughly, if I can paraphrase, the question is, well, what we know M and N, right, because they correspond to the observables of a Q nit and a Q mit. What's L in this theorem? How big is L? So there is a bound on L. L doesn't have to be infinite for this to be true. L is, I don't know off the top of my head, I think you can bound it above by m squared times n squared. So there's always, this L doesn't have to be infinite. It can be some finite number, and that finite number can be smaller than at least m squared times n squared, I think. Have to check that. Yep.
You told something like that the V is not unitary, and what did you mean with it? Because this is the definition of unitary.
The V is an isometry. So that means it's an operator where V dagger times V is the identity, but V times V dagger is not necessarily the identity. It could be the identity, but And so that's what that, you have some system of m levels, you apply an operation to it, and now you have a system with n times L levels. If m does not equal n times L, then it's an isometry in general. All right, that's it for dynamics in this course. That's the end of our quick summary of all of quantum mechanics, the axioms of quantum mechanics, or the postulates. Today we're going to move on now to the more serious business of modeling the environment part of our system environment picture. So all of this discussion up so far has been to reassure us that the way to describe systems interacting with environments is by preparing your system and environment in some state, allowing it to evolve according to Schrödinger's equation, and then throwing out the environment. So far, that's all we've done in this course. Let's say that that's how we're going to do things. But now we got to get to the business of modeling this, the environment. And that brings us to the topic of many particles. We're going to have to deal with quantum mechanical systems which have more than one particle in it, or perhaps an indefinite number of particles. So the environments we interact with on our everyday typically comprise of many, many, many particles, 10 to the 23 particles or more. The electromagnetic field in this room is comprised of zillions and zillions of photons, and we're interacting with it. So in some sense, we're going to have to deal with the fact that we've got these photons there, even if we're going to trace them out and ignore them at the end of the day. So how are we going to talk about many particle systems in quantum mechanics? Well, the first thing is we know how to compose two systems, right? That was something we already covered. So let me write out the question. That's the question we're going to concern ourselves with today. How are we going to describe systems in quantum mechanics that are made of a possibly indefinite number of particles? So indefinite means that particles can be created and or destroyed. And that's the case for very many systems. The electromagnetic field is a good example. In solid-state physics, systems where there's Cooper pairs can be created and destroyed. There's an indefinite number. There can be an indefinite number of particles. And as we go on in this course, we're going to become very specific. We're going to model the environment as a bunch of photons. The environment will invariably be, in this course, the electromagnetic field, and it will be in some thermal state. That's where we're going to go in this course. And that thermal state will be one that you can model using quantum electrodynamics, and we'll write down an actual state, and then that's how we'll model the environment for the most part in this course. But it costs us not so much extra work to talk about the completely general situation. So I can't resist doing that to give you the most general way of describing environments with an indefinite number of particles. And then basically immediately we're going to go to annihilation and creation operators and talk about the electromagnetic field. So that's where we're going. So the first step is to describe the composition of n quantum systems. You have to remember the way we do that is by the tensor product. So if we have n quantum systems, A1, A2, A3, AN, with observable algebras, meaning bunch of matrices, calligraphic A1, calligraphic A2, the way we do that is via the tensor product symbol, tensor. So So this bunch of matrices there determines all the describes all the possible observations you could make on the composition of A1, A2, all the way up to AN. That's just a reminder. But that's not sufficient for the task of describing a quantum system which has an indefinite number of particles. Indefinite means that it may have 1 or 2 or 3 or 4 or 4, 5 or so on, all the way up to infinity particles. We need to describe that using something more than just this. And the canonical example to keep in mind is the harmonic oscillator, or a mode of the electromagnetic field. If you have a waveguide in the 0-0 mode, you're stacking photons in there, one after the other. You don't necessarily have a definite number of photons in the waveguide. So you need to find some way. I mean, we need to talk about it some way, right? We need to at least write down something in mathematics that will model that. These particles don't necessarily have to be identical particles. So what I'm going to do is going to describe how to model an indefinite number of not necessarily identical particles, and then say, well, what if they are identical? How do we do that then? That's the next step. And to reduce the suspense, the answer will be Fock space. So before we get to our Fock space, we're going to talk about the Hilbert space for this composite system here. Because we're going to do things in terms of Hilbert space here. So the corresponding Hilbert space for this composite tensor product of A1, A2, A3, so on. That's just easy. We're going to give it a symbol. Now, this is my factor H. A little curl there. So it's an H. Actually, we'll do it this way first. So A1, A2. All right, so far I've said basically nothing. I'm just reminding you of how to compose quantum mechanical systems. So if you have a composite quantum systems of n different subsystems, each with their own Hilbert space, HA1, HA2, all the way up to HAN, then the Hilbert space for this composite system is just the tensor product of these Hilbert spaces. We already met that. To discuss an indefinite number of particles, we're going to build a new Hilbert space. And to make things a bit simpler, we're going to assume that each of these particles lives in the same Hilbert space, same single particle Hilbert space. So each with a single particle Hilbert space H, we introduce Fock space. So this is the Hilbert space now. We just hereby defining this. Fock space is the way we're going to model a system with an indefinite number of particles. I haven't told you what Hn is, but I will in a second. H superscript n is just the tensor product of Hn times. Where I have to give some definitions. H naught is defined to be the complex number C. Hn is the n-fold tensor product of H. So this is a space. It's a Hilbert space. So, okay. So I have to be. Do I have to worry about closing it? No. Let's not close it. Each of these H's is a Hilbert space. If you take the direct sum of two Hilbert spaces, you get another Hilbert space. This is an infinite direct sum because n is not bounded from above. So we've now, even though our little h, the thing modeling our single particle space, like might be a qubit, a two-level atom, if we have an indefinite number of two-level atoms, then the smallest space that would be able to describe an arbitrary state of that is infinite dimensional, right? Because we have to admit that there may be another atom. So if you ever had a bound on the dimension of your Hilbert space, every time you bring in a new atom, you have to have a bigger space, right? So Fock space has to be infinite dimensional. It's only mildly infinite, so I probably won't make that statement precise in this course. There's worse kinds of infinity out there, so this is This is only a little bit infinite. And so we have to, that's the space we declare to describe a system with an indefinite number of particles. Now, I think you're entitled at this point to ask why. Why the direct sum? Why the tensor product like that? Couldn't you have just written a tensor product there? And the answer is yes, I could have. That space would be bigger than this Fock space. It would certainly allow us to describe an indefinite number of particles. But it has a kind of unfortunate side effect. If you replace this with a tensor product, an infinite tensor product, it has an unfortunate side effect that it allows too many states, the states for which we can't interpret in that space. They allow things like superpositions between crazy stuff. I can't even, I don't know, if you want to stay awake at night, think about this, what on earth that could mean. So the answer is, why would we do this? Because it's the smallest space that gives us a vector for each state we think ought to be there. If that's the justification, that's the justification. So what does a state in Fock space look like? At the moment, this doesn't look like the Fock space you've already met, right? We're going to get there, but at the moment, it doesn't look quite like it. So what do states in this Fock space look like? Well, they're lists. They're basically a list of vectors. So we've got we have to have some kind of state for H naught. We have to say what that is. We have to have some kind of state for H1. And I'm going to put kets around these. So alpha naught is a state in H naught, which is just the complex numbers. So alpha naught is really just some complex number, alpha naught. Alpha 1 is some element of H, so it's like some vector. Alpha 2 is an element of H tensor H, so it's a more complicated vector, possibly, and so on. It's an infinite list of vectors, which eventually becomes 0. I won't quantify that statement. We're not going to do the full rigorous functional analysis definition in this course. So I'm going to appeal to your physical intuition. A valid state in Fock space is a list of states of these bigger and bigger systems, which eventually becomes 0. So that means as n gets bigger here in this list, those vectors have got to get closer and closer to 0. So note that these vectors aren't normalized. Okay, that's crucial, right? We don't have necessarily that these guys are equaling 1. Now hopefully in the next 20 minutes or so, I'll be able to bring this down to Earth and talk about the photons that you know about already. So this space is still too big because this, for many practical purposes. So if you want to describe a system of an indefinite number of distinguishable particles, ones that you can give a name to, like Alice, Bob, Rosemary, Eve, each of these particles has a name. there may be an indefinite number in the room, but you can give them all a name and you know who they are. Then that's the space for you. And this sometimes is the right space, but today it's not the right space. If you want to talk about photons or electrons or other fundamental particles, we know that they are identical. How do we know that? Well, because of the Gibbs paradox. So actually you can there would be thermodynamic consequences of particles not being identical. I won't go into that today. But we do know that particles are identical. If you have a photon from a Philips light bulb, it's exactly the same photon. If you set the light bulb up as a photon from some generic light bulb, there's no way to distinguish them if they have the same quantum numbers. So we want to talk about identical particles. So to talk about identical particles, we're going to observe something about identical particles, meaning that if you have two identical particles and you swap them, well, you have the same state, the same system afterwards. And the way we build the space, the Fock space for identical particles, is we start with the Fock space for not identical particles, and we simply identify all those states that should be the same. That's it. There's nothing more to it. And when you have a vector space and you want to identify two vectors, there's essentially a unique way to do that by projection. So we're going to project out everything that's not the same. You can do a quotient, but that's the same thing. So the way we're going to build this projection is we simply take we start by looking at n particles, and we project out anything where these guys are not the same, right? So same means if you swap them, you get the same thing, and that's what we're going to do. We build this linear map here, Pn plus minus where. And there's a whole bunch of stuff here that I haven't explained yet, so I better explain it. Where n is n, so I don't need to explain that. Sn is the symmetric group. So-called symmetric group of all permutations of the numbers 1 through to n. So Sn is a set of all permutations of the list of numbers 1, 2, 3, all the way up to n. So if you give a permutation a number, it'll give you back another number between 1 and n. Every one of these are one-to-one maps, so if you're given a number, you'll definitely get a number. If you put in a different number, you'll get a different number, so they're one-to-one and onto. Okay, that's the first thing I need to tell you what it is. Then what's this epsilon pi plus minus thing? So this is a character of the symmetric group. Another fancy word for saying a number. So how about I'll just define it. Let's start with E plus. That's just the number 1. nothing complicated there. If, however, you put a minus there, then you get +1 or -1 depending on All right, let's consider the case n is 3. We have some permutation which takes 1 to 2, 2 to 3, and 3 to 1. How many transpositions do we need to, and then you could draw a diagram for this. 1, 2, 3, 1, 2, 3. That's how we describe this permutation. How many transpositions did we need to make this pi? What's a transposition? It's when you just exchange two numbers. Well, we can build it with transposing 1 and 2, and then following that with a transpose between 2 and 3. I think. Let's try that out. There we go. Think of it like that, as a product of two transpositions. Yeah, that sort of doesn't work. So that's wrong, but isn't it? Or is that right? 2 goes to 1. Other way, right? Yeah. Is that right? Yes, that's right. There we go. So you can write pi, this, as a composition of two transpositions. First you transpose 1 and 2, and then you transpose 2 and 3. And according to that, E of pi is 1. If pi was just a single transposition, E of pi would have been -1, and so on. So it's either -1 or +1. So I've only defined P on these product vectors, but you can go away and check that if you extend it by linearity, you get a projection. So P becomes a projection operator. And then in terms of P, we're going to build our Fock space for identical particles. All right, then let's do it. So Bose-Fock space this is now this Hilbert space we're going to attach by definition to a system, an indefinite number of identical particles, each with a single particle Hilbert space H. And we call it F plus of H, and its definition is the infinite direct sum as before. So it's almost exactly the same as this Fock space for distinguishable particles, except we're going to apply this projection P. Oops, there's a minus there. Well, you know what? Let's do both of them at once because we can. That's the whole beauty of this notation. You can do the bosons and the fermions all at the same time. And Fermi-Fock space so basically in this course we're going to ignore fermions. We're never going to really talk about them because life is complicated enough with bosons. There are certainly situations where you'll have an environment modeled by a bath of fermions. That's what happens in metal. Metal is a big sea of fermions, and if you have some quantum dot embedded in your metal, then your environment, the natural environment as well, the electromagnetic field which couples with your dot, but also the sea of fermions that is flooded through the conductor. So there are situations where we'll certainly want to talk about Fermi-Fock space, but probably in this course, just to keep things simple, we'll just talk about the electromagnetic field. And so from the outset, I'll be kind of de-emphasizing the fermions. But everything we say in this course will be true for fermions as well. Yeah. Good. See what we're going to do now. We're going to talk about, I guess we'll talk about creation and annihilation operators. Yeah, why not? We'll do that now. And then next week we'll talk about second quantization super briefly before we move on to Gaussian states. And those are the states which probably concern most of you here. Good. So we have this gigantic infinite dimensional Hilbert space that describes an indefinite number of bosons with this internal Hilbert space H. Before I move on to annihilation and creation operators, I should give you an example, right? So an example of a single particle Hilbert space is, say, the mode functions for a standing wave of light. So think of a cavity now. Oh, man. All right, so the standing, if you just look at these mode shapes for a cavity of light, there's an infinite number, right? You can label them by integers. And the Hilbert space for a single photon inside a cavity is just some vector for a harmonic oscillator, right? It's, well, here's a fancy way of writing it. So if you like that kind of thing, that's your kind of thing. If you don't, then it's any vector psi. H is the space of any vector of this form. Psi is an infinite sum of these single particle mode shapes. And this is already infinite dimensional, right? A single photon in a cavity is already has an infinite dimensional configuration space. And when you talk about multiple photons in a cavity, an indefinite number of photons in the cavity, then you have a whole lot more of possible states available to you. So it's big, right? It's an infinite collection of harmonic oscillators, if you like. But what typically happens is if you cool things down a lot, right, and you stabilize things. I'm not the expert here. I think some of you work with cavities here. I'm not sure. At least one person does, right? If you're really, really good, right, you can get it so that all the photons are in the lowest mode. You can arrange things so that all the higher modes are not occupied. So if only the lowest mode is occupied, then all your states will live in a smaller subspace of Fock space. And I'm not going to fit it. All right, I'll erase this part of the board. So if your photons are restricted to the lowest mode, you still have an indefinite possible number of photons in that single mode. There's only one mode here. So I will continue this down on this board. I'll get rid of span by, I don't like that. All of the states you will encounter, if only the lowest mode is occupied, is Fock space built on the Hilbert space C. Right? Only one possible mode is ever touched in your single particle Hilbert space, namely the zeroth mode. You have an indefinite number of particles all definitely in that zeroth mode, but you just don't know how many there are. And is this space finite dimensional or otherwise? No, it's infinite dimensional, right? We look at the definition. But here something dramatic happens, right? Because H is now just C, it's not like an infinite dimensional space now. H is just one-dimensional vector space. This is the few places where a lovely cancellation occurs, right? The tensor product of two one-dimensional vector spaces is a one-dimensional vector space. And actually, it's these subspaces here that correspond to 0 photons, 1 photon, 2 photon, 3 photon. All right, in the last 5 minutes, I will talk about, just write down, question?
For multiple modes, is the small h a direct sum?
Yeah, for multiple modes, the small h is the direct sum. So if you know for sure that your cavity has photons in mode 0 and mode 1, but no higher, then it's the direct sum of C with itself, which is C2. But now h is big, right? It gets f of h becomes a lot bigger. super big, because now you've got an effective spin. Each photon has an effective spin, if you like. Effective spin, half degree of freedom. And now you have to say what each photon has. Is it sort of a superposition of 0 and 1? Or all right, we are running out of time for today, so I'll just write out the definition of the annihilation and creation operators. I'll write out the definition for the annihilation and creation operators, and next week we'll get into the business of modeling photon fields and things like that. So here's the formal mathematical way of doing it. Suppose you have some single particle state, like a mode shape or something like that. I'm going to define two objects. They're going to be operators which eat a vector from our Fock space and give us another vector from our Fock space. Oops, just f of h. We're back to indefinite Fock space. So whenever I don't have a plus minus here, you've got to remember that that's this indefinite Fock space. All right, this operator A, if you apply it to a vector of the form just f naught, like this first element of the direct sum, then it's defined to be 0. Now remember, f naught is an element of the Hilbert space C, so it's just a number. And if you apply a dagger to just a number, you'll get given a vector now in H. So this is how A acts on the subspace H naught. This is how A acts on the subspace H1. Now we'll say how A acts on the subspace Hn. So this will look unfamiliar to you. Pretty sure you haven't encountered Fock space looking like this before, but we will connect this with the cavity type picture soon. So if you have a vector in the subspace Hn, how does A act? Well, this way, square root of n. Now it should start to look kind of familiar. And it gives us an element of Hn minus 1. Similarly, what happens if you do a dagger on an element of Hn? Well, you get this element of Hn plus 1. So these funny A operators, which sort of look like creation and annihilation operators, but sort of not, these are the building blocks for what will be the creation and annihilation operators. So far these guys work on states of a of distinguishable particles. This is not photons here or fermions. It's just nothing-ons. Or something-ons. The way we're going to get the annihilation and creation operators that you, I hope, are much more familiar with is by projecting out everything that's not identical. And we have so these things, I hope, start to look familiar. This thing here, this F is the internal state of the particle you are annihilating or creating. So if your particle has an internal spin or an internal angular quantum number, then you can create an instance of it with this operator here, or annihilate an instance of it with this particle, with this operator here. So this notation is slightly odd. I mean, people would notate this slightly differently, and I'll show you that next lecture, I guess. But that's what the interpretation of these operators is. And they obey some relations, and these I hope will be familiar to you. I'll write them all in a combined form. So we can do bosons and fermions all at the same time for most of this discussion. So this is all super general. It's so general that we can talk about fermions and bosons at the same time. We can talk about internal levels. We could talk about a whole bunch of, we can talk about distinguishable particles. And you don't need to remember all of this. For what most of this course will be focused on is very specific examples of these operators that you should be familiar with and which model the electromagnetic field. So that'll be our main focus. We'll get to that specific example in the coming weeks. And simply regard this as some formalism that allows you to talk about all of these systems at one go without having to do it on a case-by-case basis. All right, that's it. Oh, wait, a question? Should it? Oh, you're right. Yeah, thank you. It should be minus plus, shouldn't it? Because we have bosons, which have a commutator, and fermions, which have an anti-commutator. Thank you. Yeah, that's absolutely correct. Or, okay, I guess the notation's correct, but it's not what you want. So let's change it around, shall we? So we should have done minus plus all the way through here. So that would now conform to, I guess, the standard notation that people would have for commutators and anti-commutators. All right, that's it for today. Thank you very much.